Okay, so as I was saying, divergent plate boundaries are the most common at the edges of oceanic plates. The most classic example, although there are others, is the Mid-Atlantic Ridge, which is the depiction that you're seeing here on the slide. So this image has an exaggerated ridge, of course, although the ridge itself is quite wide, about 200 kilometers in width, which is the same as 120 miles or so. The image here basically portrays it being of at least 1 or 2,000 kilometers in width. So it is exaggerated, but it does look very large. And the image I showed you some slides past does it good justice. So scientists were able to map the extent of the Mid-Atlantic Ridge sometime before we knew what it was, actually, what caused it. So actually mapping of the ocean floor was one of the reasons why we actually started searching for reasons for its complex nature. And further exploration of the ocean floor was root for 2 to 3 evidence lines for the theory of plate tectonics. Although divergent plate boundaries mostly happen at the ocean, again at the edge of two oceanic plates or two continental plates that may have part of oceanic lithosphere attached to them, it doesn't always happen. So there are cases where you can get spreading near continental margins. Currently, the most famous and perhaps the only example of this is when you have continental and continental land masses splitting from one another. You have spreading, and this happens in the Great Rift Valley, which is a location near the Horn of Africa. So right here, basically, and you see it better, I guess, in this image that is portrayed on the top right. So what is happening at the Great Rift is you have a triple junction or rifting of the African plate, right? So you have the African plate here to the west, you have the Indo-Australian plate here to the southeast, and then you have the Arabian plate here to the northeast. And those three are spreading from one another. So there is rifting going on between all of the three plates as the image shows. And thanks to that rifting, we have the opening that has caused the Red Sea, for example, the Gulf of Aden, which is, I guess, right here, and that it is currently actually causing the spreading near Lake Victoria, Tanganyika, and Lake Malawi. So all of these three lakes that are here and are pretty huge are splitting, and they are growing larger thanks to the splitting up of the African plate and the Indo-Australian plate here. And the Red Sea is being caused or being spread by the Arabian plate and the African plates splitting, and the Gulf of Aden is splitting because of the Arabian plate and the Indo-Australian plate splitting from one another. Also, another effect of the Indo-Australian and the African plate splitting from one another are the amount of volcanoes that we see in this area. So the volcanoes that we see in Ethiopia, in Kenya, Uganda, Tanzania, and then the Democratic Republic of Congo are also a cause of this splitting up in the Great Rift Valley. Okay, when you have convergent plate boundaries, you have three different possibilities that can occur, as we saw a few slides back. So you can have oceanic to continental plate boundaries, where the oceanic plate will subduct under the continental plate and cause some sort of volcanic continental arc just a little bit away from the edge of the plate, a location where the leading edge of the subducting slab would start to reach the hot asthenosphere and cause magma to rise towards the surface. So again, if you think of that scenario, it would be here is the subducting plate, here's the leading edge of that subducting plate, here's where it's reaching the hot asthenosphere and causing magma to come up and form that volcanic continental arc, right? So that would be one option. Another option you have is when you have two oceanic plates converge, in which case, the this scenario right here, in which case the denser of the two oceanic plates actually subducts underneath the less dense one, and the same thing happens whenever the leading edge of the subducting plate reaches a hot asthenosphere. magma starts to form and rise and cause the volcanic island arc that you see in the non-subducting plate, right? So a good example of this one would be the Aleutian Islands, again in Alaska, or the Caribbean islands, for example, are also a set of volcanic island arcs, thanks to the Caribbean plate subducting. And then the third option that we have is when you have continental to continental convergence, where neither of the two plates will truly subduct necessarily, but rather they will collide and build up both in elevation and down in depth, like the image that is shown. So that is what has happened and has been happening in the Indo-Australian and the Eurasian plate. So initially the Indo-Australian plate had some sort of oceanic crust or lithosphere attached to it, and so that did subduct. But once the rest of the continental lithosphere came in contact, like you're seeing right here, they simply started to collide and form up in elevation as well as down in depth. So they started building up material, as you're seeing. So in this cases, you get a lot of mountain building events, like again, our current example, which is the Himalayas. So here I'll go ahead and show you a few more examples for each of the three types of convergent plate boundaries. So a good example of the oceanic to continental plate boundary are the Andes Mountains, which are in South America, right here. So they are formed from the convergence of the Nazca plate, which is to the west, and then the South American plate, which is to the east. The Nazca plate is subducting and causing volcanism to occur in the Andes. The Nazca plate is actually quite dense, so the angle at which it is subducting is very steep. So this trench, which is this dark blue line that you're seeing, is very, very steep. And so you have volcanism going on in the Andes themselves. So the volcanism that you're seeing is mostly in Chile, but it also happens in Peru, Ecuador, and in Colombia as well. And there is some mountain formation that is associated with this type of event as part of the material that rises. It does not erupt necessarily, but it does cool before reaching the surface, and so it's adding up material to the crust basically in that location. So you have building of mountains as well as volcanism. So here is the second type of convergence where you have oceanic and oceanic plate convergence, right? In which case you have the denser plate subducting underneath the less dense one. And typically the younger plate will be the one that is less dense. So I should mention here that the less dense oceanic plate is typically younger because as it is formed later in time, it's a little bit warmer still. And by being warmer, it causes it to occupy slightly more space for the same weight. So remember what we had talked about in convection. When you have something that is hotter, the same weight occupies more space. So because the younger one has formed much later in time, it's still warmer, which causes it to occupy more space and hence be less dense. Okay. Okay, so another good example of oceanic to oceanic convergence is happens in the Solomon Islands, which is in the Pacific Ocean. So here, what happens, and it's hard to see in this image, but you can sort of see it. Solomon Islands lie here, just somewhat northeast of Australia, close to some of the Indonesian islands, I suppose. So the Indo-Australian plate is subducting under the Pacific plate, which causes magma to rise from depth. So this magma is rising from depth near the leading edge of the subduction plate. So this happens all the way down to or close to the lithosphere, near the lithosphere and asthenosphere boundary. And this causes the volcanic islands that occur in the Solomon Islands. Vanuatu being one of those, for example, that you have right here. And these are just some of those islands that are caused by the volcanism. And lastly, we have the continental to continental type of plate boundary convergence, where neither plate is subducting, but rather the material on either edge piles up together vertically, causing huge mountain building events like the Himalayas, right? So the Himalayas are the highest mountains that we have in the world. The Himalayas themselves have 10 out of the tallest 14 peaks in the world, peaks which are all above 8,000 meters. 8,000 meters is about 26,000 feet in elevation. So 10 out of those 14. Another good ancient example of this type of boundary are the Appalachian Mountains, actually, in the US, the Atlas Mountains in Africa, and the Caledonian Mountains in the British Isles, Greenland, and the Scandinavian countries. So as you're seeing in this image behind, once upon a time, those continents used to be together. So Africa, North America, and then Greenland, Scandinavia, and the British Isles used to be together. So when they were together, when they merged towards one another, they caused the mountain building event that eventually turned out to cause each of those separate islands that were mountains that we see split today. So at the time, those used to be actually the Laurentia plate, the Baltica plate, and the Avalonia plates, and are now split due to spreading of the current plates later in time. So those plates being the North American, African, Eurasian plate, basically. So the last type of plate boundary that we have is going to be the transform plate boundary, as we saw, where plates will slide past each other. So the image that you have here on the top left of the slide is an image of the Pekiang fault, which is a smaller intraplate transform fault in the northwestern part of China. But the image itself shows very well how the rock layers used to be together and continuous from the left side of the image, so this rock, for example, to the right side of the image, we used to be here, right? This red streak corresponds to this red streak over here. And we see that it has moved at least many meters due to the sliding motion of the two internal plates, I should say. So in this case, what you have is displacement laterally, not vertically, as you did in the previous example of plate boundaries. So the same thing happens in the San Andreas Fault, which goes through most of Western California, as you're seeing in the image right here. So what happens here is that the Pacific plate is moving towards the northwest, and the North American plate is moving towards the southeast. And so as they slide past each other, every time friction between the two plates is too great, and then they overcome that built up stress, energy is released through what we call elastic rebound. We'll look at elastic rebound concept later in the next chapter. But what this release in energy causes is the shift in location of certain areas of the fault. So for example, in this picture of the 1800s, or early 1900s, to the top of the right, to the top right of the slide, you can see the displacement of a fence. Obviously the fence was previously continuous, but now it's not because of that displacement, which makes the purpose of a fence pretty useless. Another larger scale picture of the San Andreas Fault results, is shown at the bottom left. So right here, you see that this side of the fault is moving north, this side is moving south, and this channel that is on the left side really connects to this channel on the right side. So you see the displacement pretty well on that picture as well. We'll talk about the San Andreas Fault in a lot more detail in the next chapter, so for now I'll leave it with that.